Welcome to this session. I'm so excited that you're here, coming to hang out with us to learn a little bit, grow a little bit. I'm hanging out with my good friend Andre Patenaude from Copeland. We're going to be diving into CO2, and this is what we talk about all the time. We travel around the world. We talk about CO2. We train CO2. We've trained tens of thousands of technicians and continue to train them consistently. We're going to have a lot of people here tonight sharing knowledge, and our whole goal for this session is teach you on the critical sensors in CO2 on CO2 systems that you need to know as a technician. You're a new technician, you're a senior technician, or if you're just getting, the understanding of what's going on with CO2, we need to know these sensors. One of the great things about CO2, there are all these sensors. I was doing a training today, just finished an 8-week course up, and the technician started to work more on CO2. And he's like, Trevor, since I started working on CO2, I don't want to go back and work on HFC systems. You know what I mean? I hear this consistently, and this is why we want to talk about it. So, Andre, welcome. How you doing, my friend?
I'm doing great. I'm loving it. Thanks for inviting me here, Trevor. It's always great to get together with you and chat and share some knowledge. I've always enjoyed it.
Yeah, no, me too. Because one of the things that I really like about you that you're passionate about sharing this knowledge. Like you really wanna help the people in the industry. It doesn't matter if it's technicians or if it's end users or if it's manufacturers. You're really passionate about helping others, and that's what I really like. That's why we get along so great. And tonight we're going to be sharing some great knowledge because I seen this presentation he did a few times at the NSRC events, and I just really want to get it out there more. I want more people to know about these sensors because it is very important. And these sensors aren't like brand specific. These sensors are really on any CO2 systems out there. All the manufacturers like the Hussmans, the Hills, the Zero Zones, Advancers, whoever it is, Teco, Vitalis, all these systems have to use these critical sensors. So I'm super excited to dive into this.
No, that's great. I mean, and I appreciate your willingness to amplify this because you mentioned NESRC and as I start talking about the presentation, it started with NESRC and I'll talk about where that came from and why I decided to build this presentation and share this information.
Okay, Andre, let's get cracking here. Let's.
Sure. Well, thanks, Trevor, once again. I'll jump right into it. You've introduced the topic, 8 critical sensors here, but I decided to use this image of a chessboard and the king down. It's very visual. The king's down, game's over. Same thing with the critical sensors, and that's really how we classified critical sensors. You can see the definition that a critical sensor occurs, when it fails, you get immediate loss of refrigeration, either one or more suction groups. So that's the definition. There are critical sensors, there are non-critical sensors, and there are informational sensors. Today, I'm just going to focus on critical. Now, talking to Brent Cheshire, who's one of our field service guys, a top guy that's done a lot of CO2 systems, and he's saying, Andre, compared to HFC systems, you could have 600 sensors on a large CO2 system. Think about that.
Yeah.
And they're not all critical. I'm going to talk about 8. So the importance of it is really important. So, and really down here, the bullet at the bottom here, such failures typically cause extended downtimes, okay? Severe operational disruptions, which necessitates the service tech to have to go there and figure out why the system's down. So that's what we're talking about, a critical sensor. And really, where this came from is NASRC. So NASRC started something called the CO2 Technical Committee a couple of years ago. And that's made up of end users. It's made up of consulting engineers. It's made up of end users. And myself, I represent Copeland as one of those manufacturers' reps. And so early on in the process, we get together and say, what can we do to educate the industry? We need to develop guidance documents so that hopefully the industry as a whole can start servicing, maintaining, and providing the same type of service uniformly across systems, right? And one of the pain points that end users had was not all systems are designed the same, and they don't all have the same mitigation strategies. And the reason that they're concerned is because if a system fails, not only is it down, you get food spoilage, you get customers that are upset because refrigeration's down. So they wanted to establish around these critical sensors that keep popping up when their systems fail, how can we educate the industry on establishing clear mitigation strategies, number one, encouraging industry-wide adoption, and I thank you, Trevor, for having me on today, and educate stakeholders. Now, stakeholders are not just service techs or guys like myself. There's OEMs, there's consulting engineers. It's the industry as a whole. If we all start thinking the same way, then we can start, addressing these issues.
Yeah.
So that's where it came from.
And I think it's important to understand this because, like you said, some systems could have 600 sensors,
Yep.
but we need to know the main ones. And it can't, there's a lot to it. I've been to a ton of startups. I do tons of trainings and I see tons of systems. And a lot of the things that I see out there, there's a lot that it's done incorrectly for CO2. You know what I mean? When I was doing training 4 or 5 years ago, when there wasn't as many systems and maybe even a little longer, there was a little bit more cautious on the CO2 systems because it was new, high pressures and stuff like that. But honestly, Andre, I'm seeing so many stores get banged in and rushed in now that things are getting missed. You know what I mean? Or things are not being done right. I don't know if you're noticing this as well, but I am getting. And so when I do the trainings, now the technicians go out there and they're looking for the things I tell them, just like we're going to talk about today. It's like, how is that actually piped? Is that piped right to the standard of the manufacturer or not? And this is really, really important because if you put the sensor in the wrong place, and I've seen this for heat reclaim, for an example, all of a sudden your system's not working properly. And then all of a sudden it can crash.
Right. Absolutely. I totally agree. And the importance of that and uniformity and following the right process is super critical. So just for the audience that are interested in this guidance document, it was just released May 6th. So that QR code, if you take your phone right now, excuse me, and you take a picture of that QR code, it'll take you right to that document. It's a 16-page document. And you can see page 1 talks about what? Critical sensors. That's the one we're going to cover today. Important sensors, but they don't cause the system to immediately fail. They could eventually when things stack up. And then you got informational sensors. And then you'll notice that even though I'm talking about, excuse me, I'm battling a cold this week. Even though I'm talking about Copeland controls, 95% of what's in this document, I'm going to be talking about today. Because regardless of the controllers, the thought process and methodology is solid. Yeah, that controller may be a little different than our control, but the methodology and thought process is the same. So I just want to make sure that that's clear.
That's important because this is like refrigeration 101. You know what I mean? Refrigeration doesn't change. You need the 4 main components. It's the same with CO2. And when and going from HFC to CO2, there's a lot of similarities. Like there's critical components in a HFC rack, there's critical sensors in a CO2 rack. So it's to really understand what they are and recognize it. It's not to change it, but you know what I mean? But go recognize it to help train other people, help train other people.
Yeah, absolutely. So the system I'm going to be talking about, and I'll be showing over and over, is this particular one here. Now, it's a basic booster architecture. And let me just walk through it because you're going to see this 35 times in the next hour, right? So here's where I'm laying it out. My medium temp compressor suction group is here. They have their own individual oil controls, high pressure switches, drive on the lead compressor. I've got my oil separator with a low level switch, discharge pressure transducer, temperature sensor, solenoid valve, oil solenoid valve. I've got an oil reservoir, so I've got a low pressure oil system with its own level control and oil system to the low temp. I'm using an adiabatic gas cooler in 95% of my images because 95% of the gas coolers that are out there today, especially in the US, are
Yeah.
adiabatic. Okay, in Canada, not as much, but in the
No, I don't. I
US,
haven't
most of
seen
them
many.
are.
I've seen a few in Canada. I've been to a few sites with a few, but it's very limited
Right.
because it's not always necessary. In a few years, I think you'll see more and more of them. But
Yeah, depending how peak energy demand charges keep going up,
yeah,
it might be used because of that. But you'll notice on here, I've got a couple of sensors, and I'll talk more about those. My gas cooler out, my pressure transducer and the drop leg, my high pressure control and valve driver, high pressure valves. Another sensor here is my flash tank sensor, high level, low level receiver flash tank sensors. I've got my bypass valve. Flash tank goes to my medium temp cases, to my low temp cases, and you'll notice I also have my pressure transducer, temperature sensor, and case controls on each, which are typical. So I didn't put sensors everywhere, but just for one and
well,
typical.
there could be 600.
It could be 600. So when you look at that system, you say, there may be one or two little things missing, but for the most part, the meat and potatoes are there. And
Yeah.
that's going to be my base architecture that I'm going forward with. So I'm talking about 8 sensors, but you can quickly count that there's 9 here because I'm grouping the adiabatic together.
Yeah.
Okay. So from a family perspective, adiabatic, I consider one. So as the NASRC, those are the ones that we consider if you do not have mitigation and they fail, your system's going to crash. So what I want to talk about is how do I prevent the system from crashing? How do I prevent it from limping along until someone can get in and fix the issue without losing refrigerant and causing the system to stop? So that's the main purpose. So,
And this is all on a low pressure system now. What we're talking about here, if you're in a 90 bar system, your chances of losing refrigerant is going to be less because in Europe the average is 60 bar, which is 800 and some psi. I think
50
60
pounds,
bar.
yeah.
Yeah. And then 90 is almost 1300, I guess. Close to 1300 and a bit and change. And so when you start to get these higher pressure systems, which we'll start to see here in North America, which are not here, we will not have to worry about relief events as much. And what I noticed too is that here in Canada, we have a lot of auxiliary units to prevent. So if one of these fails and the system crashed, we have auxiliary units. But I'm seeing more and more systems not with these auxiliary units, especially in the US. When I'm doing trainings with contractors, I'm like, where's the auxiliary unit? We're looking at the P&ID. There's no auxiliary unit to the system. I'm like,
yeah.
So
we are starting to see a trend, though, Trevor, in the U.S. Talking to the OEMs, they are starting to add more auxiliary units, but you're right. There's hundreds and hundreds of systems out there without them.
Yeah.
So
Canada's
that becomes
standard,
a bit
it feels.
worrisome.
I feel like it's a standard in Canada. Like I've been to a lot of sites here in Canada, and most of them have the auxiliary unit. And it's like some manufacturers here in Canada only sell it with an auxiliary unit on it. They won't sell it without one, right? So it comes okay, cool. So let's dive into it.
Yeah, so let's start here in the first one. Let's start with gas cooler outlet temperature sensor. So instead of having the whole system, let me just focus on T1. So T1. Now, when we're talking about Copeland, when we identify sensor T1, we call it the gas cooler out. So what does that thing do? Well, it measures the gas cooler outlet temperature as close to the gas cooler as possible. So, but when it's in subcritical mode, so it's below the 87.8 degrees, that temperature signal is used to control. So it sends a signal to the high pressure control, right? And that's one thing. And it's also calculating the TD between my pre-cool sensor 7A and my T1 sensor for fan speed. So that's number one. But when it's in subcritical mode, it's also sending a signal to the controller to say, hey, high pressure valve, you need to maintain X pressure to maintain a subcooling. Let me give an example. If I'm at, what did I say, 60 degrees, so T1 is measuring 60 degree Fahrenheit. That's equivalent to 733 pounds saturation. So the controller will control this high pressure valve to maintain 785 pounds,
Yeah.
which is 5 degrees higher than the actual temperature to throw it into a subcool range. That's a dynamic. And we're always trying to maintain 5 degrees subcooling, but it's dynamic, so it's moving up and down trying to do that. So that's one of its functions.
And one of the things to remember is like this is no different in HFC. Just remember when you're checking your subcooling, you check your pressure, your SCT, SDT, you convert it into temperature, then you get the outlet of the gas cooler to drop leg temperature, and then you convert you do your subtraction, then you get your subcooling. This is what the controller is actually doing. Just what we always did in a refrigeration system, but now the controller is monitoring that, moving the pressure around.
Right. Yeah, it's manipulating the pressure to throw it into a subcooled state. So that's subcritical mode. So what else does T1 do? Well, when it's not in subcritical, it's in transcritical mode. With our controls, when they hit 80 degrees ambient, fans are to be full speed. And we recommend fans to be at 100% full speed. So now it's 80 degrees or there. It's sensing a transcritical gas cooler outlet temperature. So again, the high pressure control indicates to the valve, okay, now you need to position yourself at an optimal pressure for efficiency's sake. So if it's measuring 95 degree gas cooler out, it's going to try to maintain a pressure of about 1,300 pounds. That's its optimum COP, coefficient of performance. If that temperature in the middle of the day goes up to 100 degrees, it's going to try to maintain 1,340 pounds. So these are integrated. Okay, so that's what it does. So if that sensor T1 fails, it typically fails open, resulting in no sensor found. And you mentioned it earlier, Trevor. If it's not installed correctly, I mean, it's difficult for it to control it. Sometimes it's just hanging. I've seen them just hanging in the ambient.
I'm doing.
It's not even measuring gas cooler.
Yeah, I'm doing trainings now. Like, so and while I'm doing a training, what I do is I get the technicians to go out and they take pictures of the sites, and I get them to take them of these critical sensors and what they look like, and they come back and I'm looking at some of them. I've seen one in a training maybe 2 months ago where they actually put the drop leg sensor inside the building at the rack with an insulation just fell right off. So, and it was he just took a picture. He's like, Trevor, look at this. And it was with zip ties. So inside, so not outside when it can get -20, on inside of the building. So that, you can run into a lot of issues because you're not actually checking what the subcooling is at the gas cooler or the condenser at this point. You're checking the subcooling inside the building 40 feet away, 50 feet away from the gas cooling. That'll cause a lot of havoc on yourself. Will it work? It will run. Don't get me wrong. It will run. But when you start to run into issues, that is probably the problem. You know what I mean? So you got to follow the manufacturer's recommendation at the outlet of the gas cooler, close as possible.
That's right. Outside. It's okay for the pressure transducer to be in the building because pressure losses are insignificant for the few feet that but temperature is very different.
Yeah, for sure.
So what's the impact of that sensor, losing that sensor, loss of fan speed control, leading to uncontrolled high side pressures and or loss of control of the high pressure valve? If that high pressure valve doesn't get a signal to tell it what to do, it's uncontrolled and then your system crashes. So there's things you can do about that. And, you can actually view through the E3 exactly what that T1 temperature sensor is reading. So this example is reading 82 degrees. It's in subcritical mode because it's below 87, right? The subcooling set point's at 5 degrees, but it's only at 2 degree subcooling. So it didn't quite make it to that 785. Excuse me. That's at we're talking a different temperature.
Yeah, but is that so at that 82 drop leg sensor T1 temperature, do you say your controller at that temperature will be 100% fan speed. Is that what you said? Was it the drop leg or the ambient air?
Ambient.
Oh, so if the ambient air hits 80, then the fan speeds will be 100%, not the drop legs and not T1. Okay,
Right.
perfect.
Right.
Okay.
Yeah, it's this sensor right here.
Yep. Excellent.
Yeah. So yeah, so in this particular case, it's measuring only 80, about 84 degrees.
Yeah.
So it's only 2 degrees subcooling, right? Which is equivalent to about 1,012 pounds of that.
Yeah.
So the information's there.
Yeah,
In
exactly.
the
This is what you got to watch, and this is the graphing. We done a few sessions before in the high pressure valve. You got to go in and
yeah,
graph this stuff and look at it.
yeah,
I've seen
right
so
here.
many. Yeah, there it is. You know what I mean? If you
Yeah.
don't, this is where you're missing the point, and you got to understand this, like understand and look at it closely.
No, absolutely. If you are having a problem and you're trying to figure out what it is, graph it, and you've got one on top of the other, so you can see what's going on with T1 temperature sensor, its pressure, the valve percent opening, all of that stacked one on top of the other. So it is a troubleshooting tool when you look at that, for sure.
Love it.
So you brought up, because that sensor is so important, it's important that it's properly insulated at the gas cooler outlet, like I'm showing here. Don't do that. Don't tie it with tie wraps on an open pipe and the sun beating on it uninsulated. That is not a good situation, because you're not going to get the right temperature. The recommendation is gas cooler out, close to it, at least 12 inches or shorter to the outlet, 5 or 7 degrees. The same kind
Yeah.
of good practice that you do when you're securing bulbs to pipes, metal clamps, thermomastic paste, waterproof insulation, and preferably white insulation, because it does have an impact on sun
Yeah.
beating on that thing, right? Um,
One of the things is that I'm working with a lot of different manufacturers, and they have different suggestions. At the
yeah,
end of the day, for me, is that you want to have it, 10 to 12 inches away so it doesn't hit an elbow, you know what I mean, from
yeah,
turbulence. I would say you should insulate it from the gas cooler to a couple feet past it, especially in Canada. In the lower states or where it's warm all the time. Okay, maybe if it's not all insulated, it's okay. But I think here in Canada in the wintertime, that coldness can affect it. If you only have there's only 6 inches on the preferred. I
yeah,
would recommend more insulation myself personally. You know
right,
what I
right.
mean?
Oh, that's a good point.
But there's lots of I've talked to a lot of manufacturers that we just want to insulate it, maybe a 10 inch piece of insulation on it, and it's
Mm-hmm.
secured properly. But I've had talked to so many people, and some people are like,
Yeah,
well, I
yeah,
like it on one side, right close at the outlet. I want it down
yeah.
past the bullhead T. You know what I mean? So everyone has their own opinions. Will it all work? It will all work if it's close and it's insulated, but it won't be the most efficient as to where
Right.
the manufacturer recommends that.
Yeah, because one of the things when you're talking about, when you're operating transcritical and the fans are full speed, they're full speed.
Yeah.
It's when the fans start to modulate. When
Yeah.
the fans modulate and you have airflow, that means that T1 temperature sensor is changing temperature all the time. So you want it to be as accurate as possible, because you've got a saturated condition here that you're also dealing with in a subcooling set point. So the more accurate you can make it, the smoother performance this will be. And in effect, your flash tank will be smoother because they are all tied. And that's just a whole presentation in itself.
Yeah, for sure. Um, but just insulating it properly. Do not just put. And I see a lot of tape. People using that insulated tape, putting it around it. I'm like,
Yeah,
no, that's not going to work. You know what I
right,
mean? You got to have lots of insulation on there and protect it, because it'll
right.
it'll fall off.
Yeah. Yeah, you don't want them falling off, that's for sure. No, no. So from a mitigation perspective, mitigation. So
Hey, wait,
immediately, so one of the
Andre, could you just explain when you say
yeah.
mitigation to everyone? Like, what do you really mean by mitigation? Because some people might not understand what you mean by mitigation strategies.
So it's having basically a solution to a problem, right? So cause and effect. So something happens, you need a plan. So in order to prevent or try to prevent that issue from happening. That's really what I'm talking about.
Yep.
And so if you do happen to have a T1 failure sensor go, ideally you can immediately trigger an alarm. You're going to see that everywhere. Number one, trigger an alarm, let somebody know. Number two, switch control automatically to a redundant temperature sensor if it's available. And we're starting to hear a lot more chatter amongst the end users that we talk about that are specifying dual sensors on the critical sections of the system. Now in the E3, it's native if the network sensor is programmed. So as soon as you get an open sensor on one, it'll default and you wire your redundant sensor to a multiplex board. The alarm's gone out. Your system's not going to crash because it's being controlled by the redundant sensor. But if you don't have that redundant sensor, what do? This is where other mitigation strategies come in. Or that's why I've got or here. Or adjust the condenser fan speed logic to control fan speed with gas cooler outlet pressure P1. Now that's going to be controlling off of a saturation temperature. Okay. So a little bit different, but you're going to limp along and still let the system, might not be as efficient, but the alarm's gone out. The system is still running, but it's running off of, and you have to build that flex combiner because now you're controlling off of a saturation temperature.
The thing is though, Andre, like at the end of the day, who cares about efficiency if you got $1 million of product on the line? Like,
100%.
like
that's exactly the end user's point. I mean, ideally, a T1, a redundant sensor would be awesome because it's the one that'll provide you with the best performance. But that's not always the case.
But there I'm seeing systems out there though. Also, the end users are trying to reduce the cost of these pieces of equipment. So it's like, what sensors can you take off? So it's like a catch-22. You know what I mean? Yep. So because I look at the print, then there's not a spec for these extra sensors, and then some I just see contractors adding them on. They're like, I know that we need this, and they just add it on. And they. And it costs a little bit, but they're like, I'm going to secure and protect their product.
Yeah, because those guys understand that if they do that, they're going to protect their customer. They just want to do a good job for their customers, so they're just going to put it on anyway, and they'll program it in and make sure that it works. But there's some other mitigation. We can move the high pressure valve to a fixed opening position. It defaults to 50%. It's native to the E3 setup, but just because it defaults to 50% doesn't mean you have to leave it at 50%, because if you know that when you're operating, that valve is kind of operating at 25% normally because it might have been oversized to begin with. If it defaults to 50%, it'll be way too much.
Yeah. So
you got to think about those things, even though there's a default. Okay.
Yeah, because a lot of controllers do that. Like I remember doing lots of SH1s and SH2 controllers. If you lose a sensor, it just go to 50. You know what I mean?
Right.
But to the default. But this is something you need to think about. And this starts at the startup, and it actually comes from the manufacturer most of the time. But we as technicians, we need to understand and go look at it to make sure it's set up in there, because sometimes it's missed.
Absolutely. I've heard that the controller gets there and there's nothing programmed in it, and the guy's going to spend days and days just programming from scratch. It does happen on occasion.
Yep.
So that's one of the things you can do. But there's some proactive things too that could be done before this even happens. You can compare reading of T1 against 7B. So the gas cooler outlet temperature measures itself against 7B, the ambient. And if the temperature reading is below ambient, if T1 is lower than 7B, it should never be lower because it's picking up heat through the gas cooler. So if it's lower, then something's wrong, either with 7B or number one. And you send an alarm, you get somebody in to check it out before the system crashes, because nothing's gone wrong yet. It's just that you've got an imbalance in numbers. Yeah. So those are things you can do.
Like
Yeah,
they go offset, and if you have to start putting like a 5 or 6 or 8 degree offset in, that sensor needs to be replaced. There's no just putting
right.
offsets in, especially these sensors. Now, if it's a case controller, okay, throw a little offset in there, but not on
Yeah,
these sensors here. You just pull a new one.
yeah, absolutely. And other things you do is compare the readings between the redundant sensors. If you do have redundant sensors, you can compare them. And if they're greater than 4 degrees, send an alarm, have someone come in, figure out which sensor is off and
Yeah.
change it so that you protect yourself in the future. And you're going to see, I'm spending more time talking about these now, but a lot of these mitigation strategies that I'm talking about right now, you're going to see repeated a few more times. So if you get them now, your thought process will be similar for other sensors. So that's what's important. Um, Consider using a thermal well. So I was at an OEM last week, and their sample unit that they were showing me, that's what they were using, thermal wells. Because
Yeah.
now you don't have to worry about that whole insulation, but it's a costlier thing to do.
I seen when I was out in Quebec, I was at a few Arneg sites. That's what they had on Ref Plus gas
Yeah,
coolers, thermal well
right.
ones.
And Goodyear also has thermal wells in some of
Yeah.
their legs. So,
Yeah, I've seen
um,
those.
and the other thing that the end users and engineers were talking about that you're going to see over and over is run the temperature sensor wiring and conduit to insulation points on the gas cooler to prevent degradation of sensor wiring due to UV. Maybe we don't get as much of that in Canada, but I can tell you go in the south, man, and that sun's beaten down over and over, day after day, hour after hour.
Yeah.
That's a recommendation that is a good one. Oh, that's for sure. So that'll
Yeah.
come up over and over as we go through this.
I love that. And that's so important because this has nothing to do with really CO2. That insulation outside, the
No,
condensing units, for a good example is condensing units. When I'm doing a training talking about condensing it, and you gotta say a keep rate condensing unit on the roof, and the pipe
yeah,
runs 40 feet across the roof and then down into the walk-in box and it's all insulated. But if it's all falling off, that is not good. It's gonna kill that Copeland scroll in the side that that condensing unit because all that heat is picking up. It's similar
yeah,
here that those UV rays will beat on insulation, on wiring.
absolutely, absolutely. So I've added this particular sensor, Trevor, since I did this presentation last. Of course, every time I look at a presentation, I change 4 or 5 things, right? So I shouldn't look at them when. But anyway, this is a good thing. Someone asked me, "What about T2 temperature sensor in low ambient?" And I said, yeah, you know what? I should add that. It might not be a critical sensor, but it's a sensor that's added to, especially in Canada, if you do, and not and northern U.S. when you've got gas cooler bypass in the winter, when it gets so cold that even at minimum speed, you just cannot control your head pressures anymore. And you enable a hot gas valve. So you're sending some gas to the gas cooler and you're bypassing the gas. As soon as you enable this three-way valve, automatically the high pressure control switches from T1 control to T2 control. So that now sensor 1A can get an average temperature between hot gas and gas cooler out and still provide the control and the subcooling set points that the system needs. Okay. So that's what that's for.
Yeah,
And
I've seen some bypass like the different parts of the world, but it's not super common yet. You know what I mean?
no,
Like it is
right.
there, but man, there's times for sure. I was doing trainings, the guys are like, they're at a rack and it just crashed because it's like 40 degrees. Actually, last week I was doing a training with the guys out in Saskatchewan, and
Oh,
they're
wow.
like, Trevor, I'm on the roof. It's minus 30 out and it's blowing 40 miles an hour the wind.
That's
It,
right.
it doesn't even matter if I have it wrapped. You know what I mean? I'm wrapping these ones with plastic and cardboard, and it's just so cold that it just can't build the pressure up, and it takes hours to
You
get it running.
you bring an interesting point because one thing that CO2 has brought up in more of these stand-up V-shaped type gas coolers instead of the slab ones. Slab ones are not as impacted by crosswinds.
Yep.
as these types of gas coolers, right? So in low ambient conditions, that one is standing straight up. To your point, when that wind's coming, you got to do something to keep the system running because all the fans are off and you got a 40 mile an hour wind blowing in that thing.
Yeah.
So
And that doesn't matter if CO2 or HFC either,
that
guys. I'm
doesn't
just
matter.
telling you, it's just too cold
we
for refrigeration.
we've been dealing with this for years.
Yeah.
That's why we know head pressure control valves well. But so similar thing, right? If if you lose that sensor, you get loss of fan speed, leading to uncontrolled high pressure because now this sensor is doing the exact same thing as T1. It's just that it's in a different position. So same mitigation, similar mitigation strategies. If it fails, you can actually trigger an alarm, switch the redundant sensor. Or in this case, though, if you don't have a redundant sensor, you can switch back to T1. Now, T1 is going to miss this hot gas flow, but again, it can limp along until you get someone in to fix it. Or, as soon as it warms up a bit, of course, you're going to be switching back to T1, but it's a limp along feature. Or you can switch to a predefined high pressure valve percent opening, again, to limp along. So there's some strategies there. Now, one
So
thing that I forgot to mention, Trevor,
yep.
I'm just talking about these strategies, but I've got Jordan, Eduardo, Mike Hill. Mike Hill helped me
He's here
understand
tonight.
the
Imagine
E3
that.
stuff related to this, right? Well, what their guys are going to do is we're going to build a deck that you're going to have someone. We're actually going to show you how to fill in those screens to set up each mitigation strategy perfectly by a QR code. So if you just want to do this one, QR code, follow exactly what's going to be done through the E3 screens. So this is where we're going with
Oh,
this.
great. Because that was a question too. It's like all of a sudden, okay, we got an alarm, but that
Yeah,
alarm has to trigger some sort of flex combiner at this point to say, okay, well, we got this alarm, go to board 2.1
yep.
and start sensing from that one versus because there's no canned programs at this point for these some of
No,
these
no,
mitigation.
exactly. So all of these flex combiners, we're going to show you how to write them
Great.
for that strategy
Yeah, that's awesome.
individually. 1, 2, 3, 4, and 5. And
Awesome.
there's a new software we're going to be using to be able to track and clearly identify and show. So that's where we want to go with this.
Yeah, because that's one of the things too. Like I see a lot of E2s. I'm doing a lot of CO2 trainings, and there's a lot of E2s out there. And like I'm going through
Yeah.
all the flex combiners, and like depending who wrote the flex combiner, it can be
That,
difficult to understand and breaking down. And when I'm going through, I use a lot of AI for when I'm doing flex combiners, and I can
yeah.
break it down, but it's still really difficult for just an average set, like an average person who doesn't do controls a lot to understand.
Yep.
Even me, it's hard. I'm like I have to reach out to different people and ask them questions like, what does this really mean? So I understand it. So if
Exactly.
you can break it down to make it easier for someone to add it, that's great.
Yeah, exactly. That's the thought process. If everyone follows that same flex combiner methodology, then if they're looking for troubleshooting help in the future, it's going to be consistent. So someone will be able to help much easier from an application engineering perspective because if they followed that procedure to begin with. So that's the thought process.
I love that.
So the next temperature sensor, the next sensor is actually gas cooler out pressure transducer, or sometimes we hear it called a drop leg pressure transducer. I'm showing it here at the gas cooler outlet line. But as we mentioned a while ago, that could be inside the building next to the high pressure valve. There's relatively no pressure drop between those 2 points, so it's not a big deal. But that sensor is super important.
Yeah.
So what does it do? Well, it measures the pressure of the gas cooler out, but again, in subcritical mode, it's used to maintain that subcooling set point. The high pressure valve moves, it measures it and readjusts to make sure that it maintains that subcooling set point. Also, in low ambient, there's a minimum gas cooler pressure that it wants to maintain, and it's going to act like a holdback valve in the winter, just like any HFC system, when the pressure gets too low, it's going to hold back to maintain that pressure, right? So that's its function in subcritical mode. In transcritical mode, that pressure transducer, again, is used when the fans are running full speed and we're trying to establish a optimum COP point. The high pressure valve is moving and that pressure transducer is measuring that. Even in heat reclaim mode, it's used to modify that. So even in the winter, we might be pushing it in transcritical mode. And again, it's measuring and adapting and providing the information for the high pressure valve positioning. Additional potential uses of that pressure transducer. Users select to control fan speed based on saturated condensing temperatures. Some guys in the field would prefer to use P1 instead of T1 to manage their gas cooler fan speed. So if you don't have access to that transducer, that's another thing that could help decommission or crash your system. Okay.
Yeah. And I've seen some of those setups, and and guys showed me graphs on the temperature outlet versus the pressure outlet, and they got it better with the pressure versus what they were doing at the temperature. But when it came down to it, it was actually there was other issues. The fans and the gas cooler weren't set up, so when they went to pressure, it made it smooth out the line more than the temperature. But I've seen there's 50, 80, 100,000 CO2 transcritical systems installed in the world using the temperature out sensor, and it works. You know what I mean? And I've heard people say, no, the pressure is the way to go. But we got 100,000 installations with the temperature out. I'm going to go with that for now. But there's a lot of testing happening out there. I see. You know what I mean?
Yeah, no, for sure. And there's different strategies of having the fans come on earlier, full speed. Then you can just rely on pressure from there. You don't have to worry about fan modulation. But those are different strategies that are beyond me at this point. But
no, but that makes sense. And what the big thing that I'm taking away from here, you know what I mean? When you think about superheat, like a TX bulb, I think about that. I look at TX. I got temperature and then I got pressure. So I got the pressure in the bulb and I got the temperature on the pipe, right? And that's it. So it's doing two things. This is not really temperature. We're at pressure right now. We're doing 1, 2, 3, 4, 5 different with this one transducer. We're doing 5 different things. So this is what you really need. This is why it's critical. It's not just doing the outlet of the evaporator for your superheat temperature or your return air or your defrost termination. It's just one thing. It's doing 5 things.
No, absolutely. And that, you may say, okay, but that one being out of control means this high pressure valve can't manage, means that my flash tank pressure's out of control, can't manage, my bypass valve doesn't know what to do, my compressors are cycling for no reason, and then it just keeps going round and round until the system crashes.
Yeah. So, I've been looking at a lot of E3s and sites through with my friend Andrew Freeberg here, one of the ambassadors of Refrigeration Mentor, and going in and just fine tuning the fan speed. I've seen so many times just clean up what's happening with the high pressure valve, what's happening with the gas bypass valve. You know what I mean? Because one thing happens, it can throw the whole system out of control. You know what I mean? And then people start playing around with P&IDs. I recommend do not touch that. You know what I mean? Like that's the last resort usually. It's usually just some setup a procedure. Now, don't get me wrong. You might need to call Mike to get some PID adjustment, but
well, you're right, because on our condensing unit control, we've taken the PIDs out.
Yeah.
They're gone. It's a different AI algorithms that we've used in order to smooth that out. But you're absolutely right. If you can smooth out your fan modulation, that means that the T1 temperature is more constant. If that T1 temperature is more constant, that means you control subcooling more accurately. That means the flow through the high pressure valve is steady. That means your flash tank is smooth. That means your bypass mass flow is smooth. That means your compressor cyclings are smooth. They're all interconnected.
Yeah.
Absolutely. And with that transducer, again, that same screen, you can find out what it's doing. You can find out what percentage valves are opening and closing, high pressure valve, bypass valve. So with Copeland, valve 1 is always a high pressure valve. and valve 2 is always a bypass valve. Okay, so that's one thing to note when you're looking at the E3. And from a mitigation, looks very similar to temperature one, right? If you got a P1 temperature pressure transducer that fails, boom, alarm sent. Second, switch automatically to redundant sensor if you have one.
Yeah.
Or if you don't, again, you can default the high pressure valve to 50% open, or you can change that slightly when you're doing your setup and then native into the E3. Or another mitigation is without the redundant transducer. If controlling gas cooler fans, you can transition control logic to utilize the discharge pressure transducer. Because you've got another pressure transducer there. Yes, the pressure will be slightly higher on the discharge side than the gas cooler side, but it gives you a pressure source that allows you to limp along until someone comes in and fixes the P1 sensor.
Yeah, and
But
the
that
big thing,
involves a flex combiner to do that.
yeah.
But it's there.
So the basically you get an alarm. That alarm will trigger the flex combiner, and the flex combiner kind of says, okay, we're not going to use P1 anymore. We're going to use discharge pressure, whatever that one is. And it makes sense, right? Because you should not have much of a pressure drop anyway. And with CO2, 15, 20 psi is not a big deal, especially, you know what I mean? Like, that's not a big deal.
Right. No, exactly. Exactly. It's a rounding error when you're talking 1,000 pounds,
Yeah.
you know.
Okay, I love that.
So, and then the other one from a mitigation perspective is you can transition the gas cooler outlet temperature to T1, but you know, you still don't have your pressure, but you can try to control off T1. So it becomes a little more complicated. The other two provides you some reasonable flexibility.
Because the whole
So
goal at this point is just to keep the system running, like you're saying, Andre. You know what I mean?
absolutely,
Like, because we still need to go and get the parts and fix it. But this here
yeah,
is, you get these alarms, you already know, okay, well, we're running up the discharge pressure, or whatever it is. I need to go and most likely bring a transducer with me. Go to the shop,
yeah,
grab one, and on your way.
yeah, yeah. So from a proactive perspective, even before anything fails, you can compare the saturated gas cooler outlet pressure while in subcritical mode to the ambient temperature. If it's below ambient, then you know you've got something wrong with the. So if this saturated, which is going to be higher again, is saturated condensing, shows a lower number than my actual air sensor, then you know you've got a disconnect somewhere. It's either this sensor or that pressure transducer. Before something actually happens, it could be coming out of calibration. But one of the things that Brent Cheshire told me, he said, man, a big problem with pressure transducers is this stress point right here. That wire gets pulled at a 90 degrees. It gets tugged, and all of a sudden you get a short in that transducer. Be careful to stress relieve that point. Little tie wraps, make sure it doesn't get stressed as it's pulled.
Yeah.
Big problem in the field. Just a little cable. So keep that in mind because there's a lot of pressure
Yeah.
transducers out there, right?
Yeah, and that's the thing. That's a thing on us, a lot of times, or the manufacturer, because a lot of times, like
Yeah.
these ones will already be on the rack. I see them being sent already on the rack, and they did just gotta hook them up, right? Or they're already hooked up, right? So it's one
Right.
thing there that we need to understand. I like that one.
Yep. So okay. So now we're only okay. We're 50 minutes and we're only at number 3, but there's more. There's some repetition, so that's good. That's good. So let's go to the other really important P2. That's my flash tank pressure transducer. Now this represents basically a static pressure. P1 is dynamic. It's changing all the time. Yes, this pressure in here changes, but it has a static set point. It measures the flash tank pressure program to that specific static set point. So if the pressure is less than the set point, if it's lower than the set point, the high pressure valve opens, the bypass valve closes, and the reverse, right? If it's above the set point, well, this high pressure valve closes and the bypass valve opens to try to maintain. And so really that flash tank it's really a simple static set point, like I said. And this bypass gas valve is nothing more than an EPR. It works just like an EPR. If you understand how an EPR works, at the outlet of a case, anything below that set point, the valve will close to make sure it builds up. It doesn't fall below its set point to keep that temperature from being at that point. It doesn't want it to go lower to freeze product. But anything above that, the valve's open. And this does a similar thing. If the flash tank pressure is higher than its set point, okay, I'm going to open, I'm going to relieve the pressure in that tank. But if it's lower, I need to close to build the pressure in the tank. So that's all it's doing.
Yeah. And that's really important because this valve here is probably one of the most important. I used to think it was the high pressure valve, but the flash gas bypass valve is probably one of the more important one because the ambient outside doesn't really change a lot unless you're in Calgary, Alberta, and it's 20 today and minus 20 at night, but
yeah, you're right.
The ambient kind of stays the same, where now the dynamics of all the different, if you have hot gas defrost, if you have cases calling, and that valve is doing a lot of work. So it's so important to make sure that that transducer is running right.
Absolutely, because that valve has a big impact on your system efficiency. Because, if you can get up to 50% of your mass flow in the middle of the summer flowing through that valve, you don't want any more mass flow than you need going through that valve, because that just means energy and efficiency loss. So that's for sure. So really, the impact of that sensor failing is flash tank pressure instability, overpressurization or underpressurization due to incorrect bypass. So, and excuse me. So that's a big one. And again, E3, you can view exactly what that pressure transducer is doing and where the bypass valve is sitting, in this case, 52%. So what kind of mitigation strategies? Again, the same as the other two, right? Set an alarm. If you've got a redundant sensor, you switch to the redundant sensor that's tied to the multiplex board. If you don't have that, then you deploy a software-based solution. You move the bypass gas to a fixed opening position. Again, in the E3, you can program it 30%, 35, 25. I mean, you can do that. Again, it's a limp-along feature that's there. Now, proactive, nothing's failed yet. What can give us maybe a heads up of a failure, potential failure? You compare the saturated flash tank pressure to my liquid temperature. Should be pretty close, right? It is a saturated condition inside of a flash tank. So if you got more than 10 degrees, something's off. It's either the transducer or the temperature sensor. Get someone in to check it out before you get a call that the system's down. Okay. So those are the three main ones related to the high pressure valves and bypass valves and gas coolers. Now, as a group, we said there's a couple more that are super important. The medium temp suction group pressure transducer and the low temp suction group pressure transducer. And their mitigations, of course, are going to be exactly the same because they both manage a suction group. So they're sitting on the manifold, of course. Failure mode, no sensor found. You might, though, have some inaccurate reading if you get some oil or some contaminant in it. So that's possible. And the impact compressor staging error or suction pressure collapse. And, compressors don't run. Of course, it's pretty obvious your system's down. So, and again, in the E2, you can see exactly what's going on with your points, your suction groups, stage 1, stage 2, and understand what they're doing. So that information is there through the E3 to look at. So from a mitigation strategy, again, same thing. If you do have redundant sensors, you can tie them to a multiplex board and just switch over. But if you don't, It's a simple solution here. You temporarily switch the sensor to the lowest SST pressure transducer on a case.
Yep.
That will get you to limp along until the service comes in to replace that pressure transducer, whether it's on the medium temp or whether it's on the low temp. If you get a failure, you don't have a redundant sensor, you go to that sensor, which is obviously has to be the lowest SST one,
Yep.
to limp along. Okay.
Yeah,
And
because it's
that's
usually
done through
like
the
2 or 3 degrees different than the header. What's the
Yeah.
actual header? So you go to the lowest one for sure.
Yeah. Yeah. So that makes sense.
And that there would be easy to set up. You got to go to the refrigeration schedule. So you look on the refrigeration schedule, you look at all your cases for your low temp, and then you'll just find either the low temp walk-in box or the low temp coffin case. It's going to say right on there which one's your lowest, and you pick that case, pick that sensor.
Yeah. Yeah. Perfect. Number 6 out of 8, oil separator level sensor. Most commonly fails open, doesn't detect oil. So again, you might have some contamination or something else that's caused the low level control to fail. And the impact would be oil starvation leading to compressor shutdown.
Yeah.
So if that particular sensor fails, you'll trigger an alarm when there's a period of non-activity, because you don't know it's failed. You just know that you're not getting any activity. The solenoid valve's not energizing to fill the reservoir up. So, and if after X amount of time, you'd have to build that in, that you would implement a time pulsed solenoid valve in order to feed the reservoir. And you've got other sensors on the reservoir, but that is something that's native to the E3 that you can do. If the sensor fails and the oil feed solenoid stays closed, you'd have to alarm and switch to the receiver level flex, release receiver level. Let that solenoid be controlled by the reservoir level, reservoir
Yep.
level.
The thing is like there's different brands out there. You know what I mean? Some are optical eyes, some are actual sensors
Yep.
in there. These are maintenance things that you need to check as well. Because if you
Yep.
go in and do a maintenance and you just change the coalescent filter, example, if that's one, and you don't go and clean that, that's an issue. That's on us, right? So you got to go and check them, take them off, clean them, because these sensors can fail. And
Yep.
there are options on there. One good thing, there's a lot of sensors on these systems. Maybe you don't even do the mitigations right. Maybe you get there and you need to just get it up and running. You can
Right.
write this in.
Right.
I like that.
The other thing I've been working on this week, I've been working on a oil control presentation, because there's a lot to oil
It's just
controls,
an
and we
oil
don't have
control,
one yet.
though.
So
It's just an oil control, Andre. Like, it needs oil, it opens up and it closes. That's it, isn't
that's it. That's it.
it?
Yeah.
That's
So
the thing about oil is crazy, right? Like I've been learning so much about oil management. Like we
yeah.
have all these depending if they're doing temperature to move transfer the oil, are they doing using the pressure to transfer the oil? Are they using optical eyes? Are they using level sense? And there is a lot to it. And it's not like just, oh, the compressor's low in oil, we'll just add oil. There's relays, there's switches, there's coils, like there's a lot to it. So take your time to understand that system that
Yeah.
you're working on.
Yeah, the timing sequence, and we got high pressure oil separators coming online now. We got 20-second fill rates. We got 120-second fill rates. So
Different
there's
orifices. So there's like, I
scissor
know like,
size orifices,
yeah,
exactly.
yeah. So like, and a lot of people don't know, oh, it looks the same. It's an OMB or it's an OM5 or OM3.
Yeah,
but inside it's got a different orifice. You know what I
yeah,
mean? So it feeds the different amount of oil when it opens up. High pressure versus low pressure is going to be different.
yeah, absolutely. So that's been fun. That's been fun. Okay, adiabatic gas cooler, pre-cool sensor. So we debated a lot on what we're going to call this sensor, but we we decided on pre-cool sensor. 7A location. That sensor is installed between the adiabatic pad. The gray here is the adiabatic pad, and the angled is your aluminum tube, your actual coil. Okay, so that's where it's positioned. It typically fails open, no sensor found. It's used to, for TD fan control. So the difference between your 7A and your T1, there's a temperature difference there when they're not operating at full speed, and you're modulating fan speed. So if you lose that 7A sensor, your loss of fan speed control could potentially lead to pressure instability, right? So how do we mitigate that? So immediately, so if you get 7A as a failure, an open contact, immediately trigger alarm notification. Now, it says switch automatic to a redundant temperature sensor, but that's generally not done. I asked the gas cooler guys. They said, no, we only put one in there. And so far, that's all that's in there. So even though it is a strategy, it's not generally done. So just kind of footnote that. So what other mitigation strategy can you have? So if you're in subcritical mode, you can adjust condenser fan speed to control off gas cooler pressure, P1. So you're controlling off of minimum gas cooler pressure, controlling off of the saturation temperature rather than the gas cooler out. Because if you lose this sensor, you can't calculate TD from those 2 points. So you're going to have to default to a minimum pressure. And that can be done using a flex combiner. You can automatically adjust the condenser fan speed control logic to a fixed minimum set point. You can say, okay, let's adjust it to a recommended 60-degree set point, for example, and the fan speed would be at that point. And that would also be a flex combiner. And you could move the high pressure valve to a fixed opening position to continue to have flow again. So there's a few things that can be done when you lose that pre-cool sensor.
Yeah. So that's a big thing, right? Because there's a lot of, like, most of the ones here in Canada, there's not adiabatic, like we talked about earlier. But what we're going to know, these sensors are super important because we know that the whole purpose of this is, like it was 2 days ago here in Ontario, it was like 33, 34 degrees.
Yeah.
Adiabatic would have been perfect because you would not have went into transcritical here during those days, right? Because you're only 4 degrees out. The humidity wasn't super high. We would have been able to probably keep that system in subcritical that whole time, for an example.
Yep.
So, but if that sensor failed, we probably would have went into transcritical on those days.
Well, it might have been. So generally, this sensor 7B that we call it is the ambient sensor. And when it senses 80-degree ambient, pretty much all gas cooler manufacturers turn their fan full speed.
Yeah. Okay.
So they have that. And depending on this ambient sensor, they also activates water at a specific point, 70 to 75 degrees, depending on the manufacturer. So a little bit different setup depending on which manufacturer it is. And I've got a little bit explanation on each manufacturer coming up. Well, three manufacturers. So some of the proactive mitigation, you can compare the reading against ambient reading of 7A versus 7B. If 7A, so the pre-cool sensor reading is above 7B, it should not be, trigger an alarm and switch to a redundant sensor. Well, if you have one, but generally you don't, as we mentioned. Other things from a mitigation is compare the reading of a redundant sensor if it's more than 4 degrees. Well, so not a lot of choice there from mitigation if you don't have a redundant sensor. 7B is your air sensor. We call it the ambient dry bulb temperature sensor for an adiabatic gas cooler. And it's used to trigger water flow. It's also used, I forgot to mention, it's also used to trigger your fan speeds at 100% when you get to 80 ambient. So if you lose that 7B sensor, Loss of fan speed control could potentially lead to instability. Prevents water activation as well. So you might be running, you need your water on, but you can't get it on. So that's a thing you need to watch for. But when you look at those sensors, one of the things I was trying to figure out, where they're all located a little bit different. This is a BAC gas cooler, and below the electrical panel, there's a little area here where that ambient sensor is that's protected from the sunlight. So it's only measuring ambient there. And as I mentioned, at 80 degrees above, all fan speeds are 100%. When you open up this little cabinet here, there's a basin down here that when it reaches right temperature, that basin fills up with water, and the circulating pump is really what sends the water up onto the pads. And you have your fill and your drain solenoid valves at the bottom of these BAC gas coolers. But that 80 degrees is that point.
Yep.
RefPlus is a bit different. RefPlus has two types of gas coolers. They've got the slab models, and they also have the A-frame or V-frame or whatever you want to call them.
Yep.
But they don't use adiabatic pads. They use a misting system. So they only have that one sensor, that ambient air sensor, if you will. And this air sensor also turns the fans on at 100% when you hit 80 degrees. But their water flow is a little bit different. You can see down here from their table that at around above 28 Celsius, the water flow starts, and it works off of a 60-second period, okay? That at 31 degrees or 88 degrees Fahrenheit, it says that you would have a 60% water flow. So they use a pulse width modulated system that 60% of 60 seconds is 36 seconds on, 24 seconds off. So you have that misting, and the moist air hits the coil, and that's how you get the adiabatic feature. So that's how they run their gas coolers. So if you lose that temperature sensor, you lose the ability to get those fans to turn at 100%.
Yeah. And that's important to understand, because these sensors are not doing just one thing. They're doing, it's not just the ambient air. Like, oh, we look at the ambient air. It's actually doing control of the system. I want to talk just about the pre-cool sensor, just to make sure that I'm clear. The pre-cool sensor is compared to the drop leg sensor, and that is controlling the subcooling while it's still in subcritical mode. Is that correct?
The pre-cool sensor, 7A.
Yep. And T1.
Against T1, so that measures a TD across that coil for fan speed.
For fan speed. Okay.
The subcooling is managed by T1 and
P1.
P1 in the high pressure.
High pressure. Yeah, sorry. So it's the fan speed control, 7A, T1. Water control is the ambient one, and the fan speed above 80.
Right. Correct.
Okay, so does it switch? Do you know if that, because right now 7A is controlling the fans when it's in subcritical. When it goes into over 80, it switches from 7A to 7B.
Yeah, you don't need the TD control anymore because you're at full speed.
Yeah. Perfect.
Yep.
Love it.
Yep. So that's RefPlus, a little bit different. Gutner, they sent me photos of theirs, and that's below their electrical panel. They have a dry bulb sensor as well. However, that dry bulb sensor for them is more informational. They tend to work off the humidity sensor as their main sensor. I don't know enough about it if the text can flip back and forth or not, but their adiabatic, their humidity sensor positioned outside the adiabatic pad, connection side or electrical cabinet side, so it can sense true humidity. The failure mode, if it does fail, it fails open And the impact is high because if that humidity sensor fails, it prevents water activation on adiabatic system. Might not be a problem in the winter, but if you're at peak 4 p.m. and it's 95 degrees outside, it's going to be a problem, which can lead to high discharge pressures, high temperatures, and in high ambient. So, and of course, if the gas cooler is sized for water flow on the hottest day and you don't have water flow, you're going to go off on high head. So that's the danger of any system that loses its water flow, because those gas coolers are not designed to operate dry at the highest anticipated ambient. They're designed to have water flow in order to meet that capacity. That's how they can keep the coils smaller. So there are some mitigation around that sensor 7B. Immediately trigger an alarm upon failure. If you have a redundant sensor, you hit switch to it. But if you don't, if the coil inlet sensor is available, turn water on when it's above 50 degrees. So if 7B fails and 7A is above 50 degrees, the recommendation is you can turn the water on. Just to limp along to make sure that if it gets warmer and warmer in that afternoon, you're going to have some protection. Or look at discharge or drop leg pressure as an alternative and turn the water on when P1 is above 900 pounds or when T1 is above 75 degrees. And that's another option. So you can switch to the back end gas cooler out in order to activate your water should you need to.
Yeah. And it's important to understand what we're trying to do, because what we're trying to accomplish here, once again, is to keep that system running. And is there any sensors in that system that we can actually pull from, data from, to be like, okay, well, we can use this information to keep the system running? That's really what we're talking about.
You're right. It's just to make anyone listening here to kind of think about exactly what you said. What else is there that I can point to in order to prevent I may not have the perfect, redundant sensors everywhere, which you won't. So you have to be a little bit more inventive, a little bit more MacGyver. What can I use? Knowing refrigeration that can keep the system running, that the pressures or temperatures are close to what I had.
Yeah.
So,
and this is so I always say, think about a case controller. So if you got 3 case controllers, it's in a lineup, they all have a pressure transducer. Think if one fails, could you use the other one beside it? For sure. You know what I mean? Like, so think about like, how do I set up a program that's going to say, okay, well, let's use case B to help case C run until we get that transducer changed.
Yeah, absolutely. And of course, retailers love that because the systems don't crash, obviously, right? And then there are some things you can do with 7B proactively. You can compare the ambient temperature and humidity readings to local weather stations. If they're way off, then you've got an issue. If that retailer has Connect Plus, then you can use the weather API with Connect Plus and compare the sensor to that. So there's some things that you can do in order to double check that. And I think this might be one of the last sensor that we're going to look at, the dry bulb on a dry gas cooler, what we see in Canada. Used to measure TD across that for fan speed control. And similar impact, if you lose that sensor, then you lose your ability to maintain fan speed control, so you have to do that in another way. So from a mitigation strategy, trigger an alarm, switch to redundant sensor. If you have one, if you don't, due to that loss of TD calculation now, because you can't calculate TD because you've lost that sensor, you can default your condenser fan logic to pressure, to P1 management. So manage off of a P1 pressure. You can also move your high pressure valve again to a default opening. That's the same one we've showed before. Similar to what I just talked about, you can adjust your fan speed logic to 60-degree minimum condensing. And as a last resort, force the fans to full speed based on ambient.
Yeah.
So there's things you can think about to keep it running, the same kind of thing. And this logic I've just talked about. So
Yeah. Because
compare.
the big
So I'm
thing,
not going to review that.
yeah, the big thing is even in HFC, like I've always done the reverse logic, you know. So if they're on ECM fan motors, we
Yeah,
always want zero volts. The fans are full speed. So if someone cuts the wire, you lose communication. Think of it like that way. And then some people don't do it that way either. I've seen lots of sites. No, 10 volts is 100%. But
right.
if you think about what's the backup, the worst case scenario is in the summertime. If the fans come on in the wintertime, it's bad too because you're going to crash the rack because it's going to drop off. But it's cold. You know what I mean? So the load for that to warm up product is going to be take a lot longer than in the middle of the summer when it's 110 degrees or 90 degrees out when the store air conditioning is not very working very well, you know. And so there's a big difference in that area. The winter time is drier than in the summertime, so more humidity, more load in the cases. So there's things that you want to think about there. And once it, hopefully, we're just jogging your ideas on how to help keep the system running because our whole goal
Yes.
is help your customer keep that system up and running and not lose a system or lose product, right? And that's what we try to do.
No, that's exactly it. That's exactly it. We've talked a lot about the high pressure to bypass valve here, so I'm not going to
Yeah,
cover that. So really, the last thing, really, but this is really my last slide, but so from an industry best practice recommendations, I mean, end users, we talked about this is what do we want to see out there to further support system reliability and reduce downtime risk associated with these sensors. Some of the recommendations are spare part inventory. You know, so I know some retailers are already doing that today, right? They're putting spare part inventory in the store. I was at a store not long ago, and they had the whole cabinet full of parts there, all the critical parts, including high pressure valve and bypass valve. So that's one thing. Start
what
specifying or using redundant sensors if you can, right? To your point, some guys are putting them in and they're doing that themselves. Um, Commissioning, and you mentioned that earlier, make sure your commissioning done right. You check, you validate every sensor before you start, especially those critical sensors. They will take you down right on startup.
yeah, yeah.
So you don't want that. Critical punch list of those sensors, preventative maintenance, double check the calibration when you go in there of those. You're not 800 sensors. There's only 8 that we're talking about that you need to make sure that they're properly functioning to to give yourself a chance or your retailer a chance and document logs and trendings of all that stuff. So
And when I see out there too, one of the big things I train a lot of technicians, and I mean I'm going training them on different end users, different manufacturers. You're gonna know some of your customers. Some of your customers are not gonna want to pay for some of this stuff. They don't do maintenance at all, and it doesn't matter. In some areas, in big organizations, some areas they do maintenance. Other areas they don't. We don't want maintenance done. You know what I mean? And
right.
systems crashing. Sometimes you can't do anything about that. You know what I mean? You want to do what's best for the customer. Sometimes they don't always see it the same way. You know what I mean? Depending who's running that store, they're just like, no, you let it just run like this until you have to really do something. And so we want to be proactive. And sometimes your hands are tied as a technician. All you can do is document this stuff. That last thing is really, really important. You
Yep.
write this stuff down in your documentation and you bring it to them. So if there's something critically does happen and they lose $100,000 of product, you protect yourself. I recommended changing these sensors. I recommended adding these critical sensors. You know what I mean? I recommend
Right.
this. So you're protecting yourself because there are some great customers out there and end users, and there's some that are not so great. And same with contractors, some great contractors and some not great contractors. It's no different.
Yep.
But what you want to do as a technician, your brand is your value. So what you want to do is
Yep.
you want to bring this up and just show them, hey, I was on this training with Andre and Trevor, and they talked about these sensors. Do you think any of these sensors would be good to install them? You know what I mean? Like, what if we come up with a
Sure.
plan over the next year and maybe we install 1, 2, 3? This is going to be the cost breakdown, you know, and some of them won't go for it. They're like, no, I don't want to pay for that. Some will, though. But you got to
Yeah.
start the conversation, right? That's the big thing. This is what it's all about, starting the conversation.
Absolutely. And once you you start using these mitigation strategies and you've got some firsthand experience on the value that it can bring to an end user, then you can talk to it, you know,
Yeah.
after you've done that. So yeah, it's
I love it. Andre, thank you so much. There are some questions here. I want to see if we can bang through them because I know I've taken a lot of your time up tonight and I really,
that's
really
great.
appreciate
Love
it.
it.
Okay, for the bam. So to switch it, is it done when you have an OL, so out of limit, a short or extreme high ohms? Is that for the redundant sensor? And I think that's it. So if you get an OL, you get a shorted sensor, or it goes out of range. That's when it will trigger the redundant sensor. So I think that's what the kind of question was.
Yeah.
Another one here is the T2 sensor. So how far away from that T should it be? So the T2 sensor. So when you're doing a
Yeah,
bypass, I guess when you're doing that bypass, is there a recommendation? Do you guys have a recommendation? Like it should it be 6 inches? And because that one should be insulated as well, right?
100% that needs to be insulated. Exactly the distance, don't have an
Yeah,
exact
that's okay.
recommendation, but kind of
Six,
a
10 to 12
probably
inches, I
six.
would say. You
Yeah, I
know,
would say
six,
6 to 12 inches, but insulated for sure because you've
strap, just
got an
like the hard.
average temperature coming from both ends. So you want to make sure that you've got enough room for it to mix properly so you can sense properly. And the bulb's got to be at that 5 or 7 o'clock as well to get good contact and
So
insulated, to your point.
yeah, just think about the how you install the gas cooler drop leg sensor, temp
Yep.
sensor, same thing.
Yep,
Okay.
exactly.
So the 7B temp sensor hits 80, it turns on the fans full speed regardless of 7A sensing. Yes, 100%.
Yeah, yeah,
Um, we had a situation where the water pump failed in the summertime. I'm guessing this is adiabatic gas cooler. What would the correct action to keep operating the system? So it depends on the manufacturer there, but a lot of them will have
yeah.
a hose fitting. So you can just go and put a hose up there and just tie it in and it just run in the water all the time.
Well, yeah. So if I back up, I think this one right here, that's the hose fitting you're talking about,
Yeah. So
right
some of
there.
them have it, maybe not on yours that failed, your water pump failed, but most of the manufacturers, Gutner, BAC, most of them will have that extra fitting to put on there.
Right,
Great
right.
questions. And if anyone has
Yeah,
any more questions, they can put it in the chat and we'll get to them later. Andre, I want to thank you so much for taking the time to do this because I think this is
that's great.
really important. These sensors here are the ones that are mandatory check on startup, but something that you need to do. Go graph some of these this week when you're out on your CO2 sites. Go look at the graph, get on the E2 or the E3, and then take a look at it, and take a look at what is it doing, what has it been doing the last day, the last week, the last month, and kind of get an idea because I know what's going to happen over the next 3 to 5 years is that, and it's already happening, is dynamic changes in these systems. 20 years ago, even when we got case control now, we run it at the same pressures year round, like the systems.
Right,
Nowadays, with all these analytics, all this data, you're going to start to see summertime set points and wintertime set points. I'm already starting to see it,
right.
and it's
Yeah,
making the systems run better.
yeah, yeah. No, it makes perfect sense with the analytics that we're getting, that we can start and the controls that we have, you can automatically set that up for under various conditions. Yeah, absolutely.
Andre, final question.
Yeah,
Um, if a technician, what is like one or two tips you could give a technician who's going to start working? If they're already working on CO2, just say they're comfortable with charging it
yeah.
and they're kind of comfortable with doing service. What is like one or two tips? Because you talk with a lot of them that you could give someone that if they go out there, that will give them either a little bit more confidence, help them learn a little bit faster, or just be able to service CO2 systems a bit better.
Yeah. Don't forget about the basics because sometimes the basics can catch up to
I
you
love
very,
that.
very fast with CO2. Be aware of, be hyper aware of your surroundings and what you're doing. So that a couple of things.
I love
Um,
that.
yeah, and I've heard you mention this many times on the controls, and you talked about it earlier. There's a lot of controls out there. There's different controls manufacturers, different ways of doing it, and unfortunately, you have to take the time to kind of sit and go through it and understand it. And it's investment initially for sure, but that initial investment that takes time, kind of gets translated job to job to job, and it starts paying itself back in huge dividends. So controls are not going to go away. They're going to get more complicated, or with AI, maybe less complicated. That's not a bad thing, but you as an individual with all these screens that you need to understand and set points you need to set, just be aware of the cause and effect of what's going on. And that's really what today was about, cause and effect
Yeah.
of trying to mitigate and get your customer to limp along so he doesn't lose product, he doesn't lose customers, because you were able to support him and help him out and guide him in the right way.
Yeah. I love that, Andre. 100%. I agree with that. And thank you so much for taking the time to do this. And if you're watching this, share this with someone. If this was helpful for you, share it with someone. This is all about learning, growing your knowledge on CO2 as not even CO2, just a refrigeration technician or refrigeration professional wanting to get better. Share this with someone because this is why we do this. Is how can we uplift the industry? We do it together. If you're interested in getting into the refrigeration mentor community, refrigerationmentor.com/hub. We got some ambassadors in there, CO2 experts from all around the world, supermarket experts that are really just trying to help grow the knowledge and share so you can level yourself up. Andre, thank you so much for taking the time. I look forward to chatting with you again on a
Yeah,
webinar or podcast or seeing you at an event like I always do. So thank you so much, my friend.
perfect. Always a pleasure, Trevor. Thank you.
Thanks, everyone. Bye bye.